As we begin our discussion on limit, let's go back to an example of maximizing and minimizing that we've done in the past. So the example here is 24 inches of wire, and you're asked to form a rectangle, but you want to make the area as large as possible. They want to know what dimensions you should use. So we start out with our perimeter, because that's what we know for 24 inches, 2 widths plus 2 lengths, and I decided to solve this for length, 12 minus w. That way, when I do my area formula of length times width, and I substitute 12 minus w in for length, here is my area formula, 12w minus w squared. Now, before I start picking things and just guessing on what width or length I should choose, I thought about the domain, and my width has to be below 12, because if I go 12 for width, I have 2 of those, I have nothing left for that length, that other side. So it has to be less than 12. And if you start picking some of these, once I get to 6, then the width and the height is the same. So if it's 5 by 7 or 7 by 5, they're actually the same thing. So I picked 6 as kind of my target for this particular example. And what I did is I picked some things that were smaller than 6, so I plugged a 5 into my formula. Then I plugged a 5.5, 5.9, and you'll notice that these numbers keep getting closer to 36. Now on the other side of it, if I go big, and I plug in a 7, plug in 6.5, plug in 6.1, these numbers are also getting closer to 36. So 36 must be that maximum area, and I get that when I choose a width of 6. So that means my length is also 6. So this process that we've done in the past, numerically, graphically, we're going to give it a name. So we're trying to find the limit of the area. What's the maximum area? The biggest area I can get, and we're looking at the width when it's close to 6. Now, notation-wise, we're taking the limit of this function as w approaches 6. And we found out that the biggest area I can get is 36. That's dimensions of 6 by 6. So that takes us directly into the definition of a limit. The formal definition says if f of x becomes arbitrarily close to a unique number L as x approaches c from either side, then the limit, what we're trying to define, of f of x as x approaches c is L. And here it is in notation form. So the limit of the function as x gets closer to c is L. Now there's a couple things that we need to discuss here. We need to discuss what this means, and we need to discuss what this means. So as x approaches c, you have to think of it from both sides. So whatever our target is, we have to look at it from both sides. And close to does not mean, if I'm looking at 6, I look at 3 and 4 and 5, or 9 and 8 and 7. If I'm looking at 6, I have to get close. So I have to look at things like 6.1, or 6.01, or 6.001. I have to get close, not arbitrarily big numbers. So there's 3 ways we're going to do these problems. The first way is similar to our example. We're going to do them numerically. So this says I want to find the limit of 3x minus 2 as x approaches 2. So 2 is kind of my target. I'm trying to figure out what the limit is there. So I picked some things smaller than 2, 1.9, 1.99, 1.999, things that are really close. And I noticed that these numbers get closer to 4. Now on the other side of this, I picked 2.1, 2.01, and 2.001, and I noticed that those numbers are also approaching 4. So the limit as x approaches 2 must be 4. That's numerically. Now let's take a look at one graphically. So in this example, I picked out the limit of this function as x approaches 1, and I graphed it. Now there's a couple interesting things about this. Let's start off with the basics. We're looking at what happens as I get closer to 1 from both sides, but I'm not going to start way out here. It works, but I get these really big numbers that don't tell me a whole lot. Same thing over here. If I start on the left and I start way over here at -4 and -3 and -2, it's going down, but then when I get to 0, it starts coming back up. So we're going to look close. So think about zooming in on a very small window and seeing what happens. Now on the right side, this thing seems to be approaching this point right here, and on the left side, it's also approaching just from the other side. So as we get closer to 1, it seems to be approaching 2 for the function. Now the catch is, I can't plug a 1 in here because I would get an undefined situation. But there's a note that says the existence or non-existence of f of x at x equals c has no bearing on the existence of the limit of f of x as x approaches c. So it takes care of this problem of, even though this point doesn't exist on the graph, I'm not worried about what happens at that point. I'm looking to see what happens as I get close to that point. And it sure looks to me like this thing is approaching 2 from both sides. Now, the strange thing that we do when we start talking about limits is we don't define all limits. We talk about the situations where limits don't exist. And there are 3 of these that we're going to discuss that cause issues. The first one talks about f of x approaching a different number from the left as it does from the right. The easiest one to talk about is a step function. So this one right here, this is a step function. We're looking at the limit as x approaches 0. And notice up here, it's approaching a positive number. But down below, it's approaching a negative number. And if it's approaching a different number from each side, it does not have a limit. I cannot evaluate this limit. The second one we talk about is when things increase or decrease without bound. This is your asymptote. My function here is getting very close to the y-axis, but it's never going to get there. So these y values keep getting bigger and bigger and bigger. It works if it's pointed down. If this had a negative and it went down, this thing would get smaller and smaller and smaller, but it's not approaching a specific number. So it increases or decreases without bound. The last one comes to us from trig. This talks about oscillating behavior. When things oscillate, they kind of bounce between 2 values. So in our example over here, this sine function, if I start plugging in a value over here, I might get a positive 1. But if I get a little closer to 0, I get a negative 1. I get closer yet, and I get a positive 1. But then I get closer, and I get a negative 1. And so I keep bouncing or oscillating between 2 fixed values, 1 and negative 1. If it bounces and oscillates, but not getting closer to it, then we don't have a limit for this one as well. Now, the last method we're going to talk about is direct substitution. Now, direct substitution tends to be the most convenient or easiest way to do some limits. Direct substitution says if I'm looking at the limit of a function as x approaches c, then I can just plug c into that function, which usually works, but not always, and we saw an example with the graphing. So if I'm looking for the limit of x squared as x approaches 4, I'm going to plug the 4 in for x. This has a limit of 16. If I'm looking for the limit of x plus 4 squared as x approaches 3, and I directly substitute that 3 in, this has a limit of 49. I can do negative limits. This is approaching -1, so I plug in a -1. I get -6. I can do fractions. I'm plugging a -1 in for all the x's. I get -3. So we talk about numerically, graphically, and directly substituting in order to evaluate these limits, and we only have 3 examples where they would not exist.